Hi, everybody. I am introducing Lance Ransom. Lance was a former partner and CTO at Schonfeld and has managed a proprietary trading group that used machine learning techniques. Lance is currently the product manager at Continuum Analytics, and we'll be talking about dark data.
All right. So to begin with, we'll talk a little bit about what is dark data, because it's one of those things that most people don't necessarily understand it. There are lots of different definitions for it, so we'll talk about how we think about it. So essentially, as companies are in business, they are collecting large amounts of data. And then they're processing this data, they're creating derived data sets, and then they're basically making that available to their employees inside their company. And essentially, as you go through that process of like going from the collection and processing, and then from processing to the actual end user, you're typically going across boundaries. And those boundaries are going to be changes potentially in how data is stored. There's going to be extrapolations, there's going to be normalizations, and you have essentially loss. You don't necessarily have visibility into what those transformations are doing, and you don't have visibility into the data set itself, and so there might be nuances and subtleties that you lose. And then by the time I'm the end user, the person over in the far right, I basically don't have a very good view of the world necessarily, and I've lost context on all of this underlying data. So in the business of trading, these are examples in terms of data sets that firms generate themselves, as well as data sets that they are acquiring from vendors. And so everything from trade history to signal histories, log files, and clearing data is another one that actually amasses, and people don't really think about that as data to be mined or analyzed, but inevitably, in the fullness of time in a trading business, you'll have to go back and reference that data. And then vendor-generated data, this is probably the data that people are most familiar with in terms of reference data, corporate actions, models, et cetera. And most people don't think about this necessarily as dark data, but going back to the previous picture, if you're an end user, if I'm at a large bank, investment bank, for example, by the time the data gets to me, it may not be what it was at all. And so although it's not dark to my organization, it's actually dark to me. So what are the challenges around data in general? The first is that it accumulates very quickly, right? I mean, some of these data sets are very large, and you have to find storage. So large organizations that have lots of geographies where they're trading, where the people that need to analyze it, they may not have proximity to the data. How it's stored varies. You could have some data sets that are in flat files, some data sets that are in databases, and also vendors change over time. For example, today I might license reference data from a particular vendor, but 5 years ago I licensed that data from somebody else. And so now that raw data that I ingested from the vendors is fundamentally different. Even if I have the same vendor, there's a high probability that over a 5-year time span, that data set itself has gone through changes. The worst part about all of this is that, in my experience, the usage of all of this data tends to be ad hoc. I mean, I think that most people would like to think that there are nicely engineered processes that are deployed and managed, and that is true, but most of the usage of dark data is for one-time ad hoc analysis. And of course, when that occurs, it usually needed to be done yesterday. So what happens? So an example scenario that I encountered, we were looking to basically change our clearing firms. And so I went to our Quants, and basically I wanted an impact study on short availability for the last decade of our trading. Meaning, if we had been with this clearing firm B rather than the clearing firm we had been with for the last 10 years, we would have completely different inputs from the clearing firm. And so in order to do that, that person had to go and find that data. That person had no familiarity with it, had no idea where it was. Then once he found it, he had to go through a process of creating an ETL because it wasn't in a form that he could use. Then that meant he had to move it, he had to copy it, he had to store it somewhere else before he could finally do his analysis and then generate a report. And this is the type of pattern that you see over and over and over again. So in this environment, this is not a contrived environment. This is actually the environment that the quant that was conducting this analysis worked in. And as you can see, it was relatively complex in terms of all the different places the data was stored. These databases were located in different geographies. And the ETL processes he didn't necessarily have access to. So if somebody had Java code or C++ code, he may have no idea what that code is doing when it goes out to the underlying data, and it basically brought in a representation for him. And the quant typically wanted to work in Python or MATLAB. Sometimes, oftentimes now, more often than not, I guess, they actually quants are capable of going through this entire stack, but it's not necessarily what they want to do. So one of the things that we like to think about is basically the notion of promoting the idea of how to describe your data, how to create expressions on that data, and then how to compute that data as independent first-class citizens. And what I mean by that is if you think about a SQL database today, if I'm going to use MySQL as an example or PostgreSQL, then I basically have adopted something where all three of these are dictated and defined for me. So I describe my data in SQL. If I want to do any kind of transformation on it, or expression or query, I have to do that within SQL, and the computation obviously is done in that one place. And what we are working to achieve is basically separating those concerns so that each of those can be done independent of the other. So the first thing that we had to do was create a way to describe data independent of a specific implementation. And that is called Datashape. It's an open source project. And essentially, it's much like other ways that you have seen data described in SQL or in Python, so it's definitely familiar. You basically have a way to specify a D type and give it a dimension. You have a way of collecting those into a record or a structure, and then you have a way of describing a table of those things. So this is an example for daily bars. And this, as I said, although it looks familiar, it's not actually, it's a language that's specific to itself. And it is not dependent on writing SQL, Java, or C++. Or it's also not dependent on where your data is stored. So how does this get used? Continuum has open sourced a project called Blaze. And Blaze is essentially the expression part of that trio. And what it allows you to do is write your expressions in Python, and it creates a Blaze expression that then you can move to where you want to compute. So if your data, for example, is in a SQL database, then your Blaze expression will get translated to SQL, move to that data, and compute. If it's in flat files, then it will use NumPy or Pandas. We also have connectors to KDB as an example. So you can write a Blaze expression that gets translated to Q and actually executes on a KDB database. It's a lot easier to move the computation around than the larger data sets. Blaze is also lazy in its evaluation, which makes it much easier when you're actually constructing these, because it allows you to build your expression, and you can build your expression on smaller subsets of data, and then essentially apply that expression to any data set. So as long as the data shape matches. So in other words, if I have an expression that wants to do something with daily bars, I can create that in the absence of data completely, and I can just say this is what a daily bar is, I can create my expression, and then any data input that matches that, I can then compute that expression against. Here are some examples of ingest for data sets within Blaze. And so essentially, in all of these result in exactly the same thing. If my data was stored in flat files and CSV, the first line would bring it in. Each of these basically brings the data in, and then the resulting bars Blaze object that I get, if I requested the data shape from that, I would get exactly the same thing, even though the underlying data is stored completely differently. These are some examples of Blaze expressions, just to give you an idea. So you can obviously do selections and filtering. You can do reductions and groupings. So text matching, and you can essentially do transformations that calculate new columns, and we'll do some of that in the actual live walkthrough. As I said, this is just a small sampling of what you can actually do with Blaze. Now, what's interesting is one of the things that's important about Blaze is that you're not locked into it. So if you're wanting to do something predictive in nature, for example, Blaze is not necessarily going to accommodate that, but Blaze can basically get you to a point where you can bring your data out and then do predictive analytics on it. So let's talk about flat file repositories, which is kind of one of the essence, one of the key things in dark data. So again, in my experience in fintech broker-dealers, is that you have all of these large data sets coming in, and most often those are delivered in flat files. And you end up over time with lots of directories and lots of files. I don't get to choose that because a lot of times the vendor will have synchronization processes where they basically say this is the way the data needs to be stored so that we can properly ensure that you are updated correctly. And the actual naming conventions of the directories and of the files is actually part of the data set. And we'll talk a little bit what I mean about that in the next slide, but as an example, let's say that date, let's say they're organizing by date. So you have year, month, and then day as a directory hierarchy. Then oftentimes they won't actually put the date in the actual underlying data set. So that is something that you have to do as an analyst or as a quant in terms of as an ETL process to munge that and bring that together, and which then basically means you have another copy that you need to store. Which is where we get to that point where now if I'm doing ad hoc analysis, I have to basically write all of these one-time scripts, which then become somewhat of a maintenance nightmare in and of themselves. So here's an example. This is a real data set for market data. And essentially, the hierarchy is pretty straightforward. Daily data, US is basically a region. And then the NASDAQ obviously is the exchange. And then there's this arbitrary 1 and 2. And I'm assuming they're just doing that because some operating systems have limitations on the number of files they can put in a directory. And then within that directory, you essentially have a file for every symbol. And for US equities, this amounts to about 8,400 files. Inside the file, this is an example of what one of the files looks like. And for AAP, and the thing to note here is the fact that AAP is not actually in this. So if I just did something where I concatenated all these files together, that's not very useful because I would have absolutely no idea which particular symbol one of these daily bars related to. So Lux is a new capability in the Anaconda platform, and essentially what it does is it allows us to describe this. So we have a very simple URI where basically we say here is a directory structure, and then we have a way to describe both the directory structure as well as the actual file name itself and extract that seamlessly into the data set. So in the Lux data set below, you'll notice that we extracted the region and we also extracted the symbol. Now what's interesting about Blaze, when it does this, it did not actually copy and store the data. It stitches these files together in real time and basically delivers to you what looks to you like one data set, although you're basically piecing that together across the 8,000 files.
Can I ask you a question real quick?
Yes.
So you said this is lazy evaluated?
Yes.
Therefore, if you're looking at, let's say there's a daily file for each stock,
Yes.
then I'm only going to be pulling those off the hard drive into memory when I call for that time period.
Correct, when you want to compute.
Okay.
Yes, exactly. Right. So just to recap, what we did is we combined the files. We didn't have to have a one-off script to do ETL. We didn't have to store it in another location. We were able to incorporate part of the name into the actual data set itself. And the other thing that this allows Blaze is it actually allows Blaze to do optimizations on the computation. So for example, if I was doing some analysis on the S&P 500, and when I construct that at some point in time, I'm going to do a join against some sort of reference data that tells me whether or not a stock is in the S&P 500. And then Blaze knows to not go touch all of those files that aren't related to the symbols that I care about. So then that means, like to your point, in terms of the files that are on disk, I'm only going to go get the files I need when I need it.
So that's assuming that the query data set is smaller than the resources of the box that you're operating from?
Not necessarily, because it would also depend on the store, right? So because Blaze can actually operate on SQL databases as an example.
Okay.
And so if the transformation that you're doing is going to SQL, so I'm sorry, in the Lux case, you're correct, yes.
Okay.
In the Lux case, ultimately, today, you'll have to bring it into memory to actually do the computation.
Gotcha.
Because in this case, you're actually relying on pandas.
Gotcha. But otherwise, there are situations where you would actually, the command that you're doing, if you're doing like an average, that would be executed into the database, and the database would be the execution environment and not the...
That is correct.
The Python environment.
That is correct.
Okay.
Yeah, that is the essence of what Blaze does.
Gotcha.
Yes.
If you're joining across different storages, would that also be an optimization boundary?
Yes. And so that is one area that historically Blaze has not had any support, and we have done some preliminary support for moving data between stores. In the fullness of time, that is definitely something that we will incorporate in terms of understanding and basically building heuristics on how long the compute takes versus how long it would take to move the data. These are all the things that I have, almost daily discussions with the developers on. Yes.
So Lux is assuming that all of the information we need to parse something as an individual record is contained within that file path. So let's say something like the year that something happens is contained within the file. We
Yes.
have to walk all of the files in order to get that information. There's no like caching of something specific.
Well, there is caching built into Lux, but you are correct. Well, in terms of if it can't optimize that. So in other words, in the example that we had with the symbol being part of the outer part of the data set, we can optimize the compute on that. If you're actually going to be doing selections or filtering based on something that's inside the actual file, then you are correct. We would still need to walk the contents of each file. Yes. Now, having said that, one of the things that we're building into the Anaconda Mosaic is essentially the notion of downsampling, where for larger than memory data sets, you will be able to basically downsample it using different means so that this problem of I can't fit it into memory and I don't want to actually go touch it, well, I could say, well, go out and bring me in a sample of this data set that I can have in memory, and I can start to explore, I can build expressions, and then basically, as I gain confidence in my expression, I can move it to the larger data set, so that you're not always having to touch the larger data set.
So you're just like reflective D-shape off the sample?
Yes, that's exactly right. All right, so Anaconda Mosaic. So Anaconda Mosaic is part of the Anaconda platform. We are in the process of going to early adopter on it. And the idea behind it is essentially to bring together all these different pieces that Continuum has been working on in the open source community. There are some other projects which we are sort of implied in this, but we didn't necessarily talk about them. But the point to Anaconda Mosaic is to give users a place where they can do interactive exploration, an actual user interface. And we're also incorporating visualizations through our bokeh and data shader projects. And the other thing that we're doing as part of this is actually starting to allow users and groups and organizations to catalog their data sets. So now when I have a data set or I have a transformation, it can be tracked, and then when we start to build off of each other, we're actually tracking when my expression relies on your expression, for example, and we're going to keep provenance features and governance features in terms of permissioning as well. All right, any questions before we get to the more fun part? All right, so this is Anaconda Mosaic, and it is sitting on top of Blaze. It's sitting on top of Lux, sitting on top of bokeh, and also another project that we call Odo, which is something that helps to facilitate moving data around. So like, for example, if I want to move data from a SQL database to a CSV file, Odo can help finesse that problem. So what we're looking at here is I've selected this index SQL. This is an actual SQL database. And what it contains are point-in-time constituents for an index. So each row in this is essentially nothing more than a symbol and a date, meaning that the symbol was in the index on that particular date. It's not particularly big. You see over here on the right, we have the Datashape, and it's only about 1.5 million rows. The next data set is actually a Lux data set. So what this is this is actually the same data set that we were talking about earlier in the presentation. So this is when we loaded this, essentially what it took downsampling of that data set. There's about 100,000 rows that I have in memory, although the actual data set is about 5.5 million rows. And it stitched them together, just as we discussed, and you can see that I have a symbol column, which is essentially the symbol for from the actual file name. I also have a Lux data set for the New York Stock Exchange, which is the same thing except for it's overlaid the New York Stock Exchange directory. So in Blaze, what I want to do, let's say I want to basically concatenate these. So here I have a Blaze expression that basically just does a concatenation of these two data sets. And now I have one table that has all of these data sets at about 13 million rows. You can see over on the right, we're tracking basically the dependency graph. So I have an ancestry tree for this particular expression. Who made it, the URI for it, and a description. So now I want to do something a little bit more interesting. And I pre-built these just because if we built all of these from scratch, we wouldn't have time, and we're going to actually build on this one. And what this does is this actually joins my SQL database of my point-in-time index constituents with my all stocks, so that now in this table, excuse me, all I have are bars, daily bars, from for the constituents for this index. Another thing that I had to do in order to join these is in this original SQL database, if you notice, we have an uppercase symbol, whereas in the Lux data sets, we actually have a lowercase. So part of what I needed to do to bring those together was actually do some munging in terms of making the one symbol set uppercase before I could do the join. And again, just to reiterate, this data set doesn't exist separately. So this isn't stored someplace. It's basically assembled when the index is computed. Any questions so far? And then I have my new data shape for this particular. So this is basically the data shape of the result of my expression. So let's go ahead and make a new data set. So what I want to do is I want to take these daily bars for this index. It happens to be the S&P 500, and I want to create a volume-weighted average price index instead of the typical market cap. So the first thing that I need to do is basically call up and do a transform. So what I'm going to do is I'm going to create a new column. Oops, and my new column, I'm going to multiply, and keep it simple, the volume times the close. So when I hit the preview button, now it will go out and basically, across the entire data set, it is now calculating this new column.
So this is pretty much an ETL solution plus Tableau.
Yes. Yes, I think that is one way of describing it. One of the things that you also get is, because you're in the Python stack, you have what I call the escape hatch, which is basically this idea that, for example, I can escape out to just Python itself, and I can do predictive things as an example. In fact, that's actually even integrated with the app, where if I have a data set that I want to work with, I can just click and open in a notebook, and then I have a Jupyter notebook with that data set.
Nice.
Okay, where were we? So we have a new column. And then the next thing that I want to do is I actually need my VWAP. So I'm going to do a by, and I don't really remember how to do my group by. So I can ask for help, and I get some Blaze help. If that's not enough for me, I can expand it, and I get more information, and then I can actually click out and go to the Blaze documentation if I was connected, which I'm not. So what we're going to do is go ahead and group. So we want to group by on the date, and we're going to create a VWAP, and we're going to do we're going to take the sim total, we're going to sum that, and then we're going to divide that by the sum of the volume on that date. And then just for good measure, let's go ahead and pull over the total volume for that day. Let's see, did I make sure I don't have any typos here? Okay, so we'll go ahead and preview that. Oops. So did I rename it? Oh yes, that was nice. So the autocomplete in Safari got me. All right. So I had a wrong column there. So this is going to compute a VWAP and a total volume on our S&P 500 constituents with point in time.
Does that intelligently cache the previous 3 steps and then only additionally compute the 4th?
Yes, when it can,
Okay.
and memory permitting. So now we have basically the data and the steps that we use to create it, and now I can commit this, and we can call this index VWAP, and commit that to our catalog, and now we have a new data set in our catalog that somebody else could derive their work. And again, this data set is not actually created and stored somewhere. It is generated in real time. And to answer your question, you'll notice that when we clicked on that, it came up very quickly because it actually had it cached.
So it's like a Dockerized.
And it knew basically it could just pull that in.
Gotcha.
Can I connect a Blaze client to these data sets?
Yes, and that's exactly, so when you do open in a notebook, then basically now I'm in a notebook and I can run this, and that actually connects to the Anaconda Mosaic local server, and you can basically pull out those data sets. And if it's a data set that has an expression, in other words, it's not a ground truth data set, it will run the expression and then return you the result. And you can also then, for example, so you could do something predictive after that. The other thing is you can also continue to build on that expression, because what you're actually getting back is a Blaze expression object. So then you could actually continue to build on, and from this interface, actually commit that back to the catalog.
And this will play nice with Odo, we can just like Odo this into something else.
You can do that. I do that almost daily. Yes. So Odo, I kind of, in the final slide, let me go back over here. Yeah, I had Odo on here. I should have, but it's just part of the Blaze ecosystem. And originally I had all of the relevant projects, and people were like, why don't you just tell them to go to the Blaze ecosystem? Other questions? Does this solve an interesting problem to people?
So is Mosaic open source along with the other things, or is that?
It is not.
Okay,
It is not.
that's what I would expect. But the piecewise defined tools are.
Yes, that's exactly right. Yes. And so Mosaic is basically the thing that brings it all together.
Right, for a non-developer.
Yes. Now, if you're an Anaconda subscriber, it comes with that. So it's not, so basically you have Anaconda free, you have the pro version, workgroup, and enterprise. If you, with the top two tiers, you would get Anaconda Mosaic just as a capability on that platform. It's not something you have to pay for in addition. Other questions?